Hello and welcome to a tutorial I've entitled the solved example of a first order differential equation reducible to first order linear equation. Right, let's start by recalling what a first order linear equation was. I'm just going to solve one example here just to give you another kind of a tutorial on solving these types of exercises. And we recall that an equation of this form, or in other words, this general form, let's say dy dx plus p y equals to q. We said this equation was a first order linear equation, and we recall that we said p here was defined as a function of x. Similarly, q, that is the right hand side, was also given as a function of x. And in our discussion, we arrived at the fact that we needed an integration factor in order to solve this problem. And the integration factor was an expression was a function of x actually arrived at by means of p. So that integration factor, say to continue it by r, and this r, the resolving factor, comes from p. So we said we could calculate this expression of x as e to the power the integral of p of x. And after this, we arrived at the conclusion that actually the solution y here, the unknown y, was going to be arrived at via the equation y multiplied by the integration factor equals to the integral of r of x multiplied by q of x. So this kind of integral equation is the one which was going to actually to deliver us the expression for r. As you can see here, we'll have to carry out this integration on the right hand side, and then after that simply make y the subject of formula by dividing both sides by r of x. That will be the function. Now we also looked at an equation which is more or less similar or exactly the same like this one on the right hand side, but different on the left hand side, which we called Bernoulli's equation, or simply an equation which is reducible to first order linear. In this case here, this was an equation of this nature: dy dx plus py equals to q multiplied by y to the power n. In our discussion, and we introduced you to that, we can solve this equation by carrying out some kind of substitution. In this case, our discussion led us to arriving at the fact that we can actually reduce this equation to first order linear by simply taking a helping variable z, which we take as z equals to y to the power 1 minus n, and then we would then find the expression for dz dx. As you can see, y according to this is a function of x, and now if we define z here in terms of y, and it's clear that z is also a function of x, so we can say dz dx, that is justified. Then that would come as 1 minus n multiplied by y to the power 1 minus n minus 1, that is applying our power rule there, multiplied by dy dx as a derivative of the argument of the power function here. So with that substitution, we saw that we would reduce this equation to first order linear, but now it will be first order linear in terms of z. Then we would solve that equation for z. Then after that, substitute z with what we get here in terms of y. Then you get this solution. So what I want to do now is actually to carry out the whole process by showing you, doing one example. Actually, one of you asked me to do the following example, number 1. So I'm going to explain number 1 here and sort of show you how we arrived at the solution which I've got here. So let's continue with that. So now having this, now let's continue with the example. The example is given as follows. is dy dx plus y equals to y to the power minus 3. And actually, according to this Bernoulli equation, which we have here, we can see that in this example, our p is 1 and our q is 1, and that's not a problem. And they were given initial condition that y at 0 is actually equals to 1 over 3. I would prefer to use my numbers this way as a common fractions, because it's easy for me to do that instead of changing this to decimal. So what I'm going to do now for the solution, so now given this equation, let z be equals to y to the power 1 minus 3, which you can clearly see that it simplifies to y to the power minus 2. Then after that, we find an expression for dz dx, which will come out here as minus 2 y to the power minus 3, applying again power rule, dy dx. So now what we notice now is this expression dz dx, there's a new factor here which is multiplying dy dx. So we'll actually take this factor and multiply this given equation here. Then it will look as follows. Now if we simplify this, you will see that here in this term here, we're going to get y to the power minus 2. And that y to the power minus 2 is actually z. And then this side, we get y to the power 0, which simply gives us 2. So at the end of it, looking at that carefully, we see that this is actually expression dz dx plus minus 2 z equals to minus 2. So at this point here, we can see that we've arrived at our equation, which is first order linear in terms of z, where p of x is our constant function minus 2, and coincidentally, our q of x is also minus 2, and there's nothing wrong with that. So then, what we can now proceed to do is to find our integration factor, which is denoted by r. Then we say now our integration factor, r of x, is equal to e to the power of the integral of minus 2, which simply we can see that gives us e to the power minus 2x. So now this is our integration factor. The solution now z, because here now our unknown is z. The solution now z is going to be given by the equation z multiplied by e to the power minus 2x equals to the integral of the integration factor, which is e minus 2x multiplied by the right hand side of the equation, which is minus 2, which actually is a simple integral, because it's actually a standard integral, or where we're actually having more or less something like this. We're integrating e to the power of f of x multiplied by the derivative of f of x, which is, we know standard, that integral will simply be e to the power f of x plus c. That you must have in your mind, and that's what you're supposed to know. So applying that here, we'll simply get this as e to the power minus 2x plus an undetermined coefficient c. So then proceeding here, we'll then start here where we've got here z equals to e to the power minus 2x equals to e minus 2x plus a constant c. So then dividing both sides here by e to the power minus 2x, which is actually the same thing as multiplying both sides by e to the power 2x. You can do any with 2, you get the same result. Dividing by this term or multiplying by that will get you to z equals to 1 plus c e to the power 2x. So now we've got solved the equation, the first order linear equation in terms of z. We've solved, we found z. Then at this point, remember we're given an equation where the unknown function was y. So we need to arrive at a point where we can express, possibly explicitly, y as a function of x. So for that, we need just to recall that we said z was equal to y to the power minus 2. So substituting that here, we simply have got here 1 over y squared equals to 1 plus c e to the power 2x. I'll write here as over 1, which does not change. So at this point, I would like to invert both sides of the equation, then get y squared equals to 1 over 1 plus the c e to the power 2x. And then applying the square root on both sides, we arrive at the fact that therefore the general solution y is equals to 1 over the square root of 1 plus c e to the power 2x. I hope you remember that if we've got a square root of a over b, that is always equal to the square root of a over square root of b. That's what I've used here. Square root of 1 over the square root of the denominator. That's what gives us there. So there, we have found our general solution. This is our general solution. And now we remember we're given that y at 0 is equal to 1/3. So we need now to use this condition in order to find the unique solution. Remember we're given that y at 0 is equal to 1/3. So we now have to use this and find a unique solution as required by the question. So let's do it this way. So we are given that y at 0 is equal to 1/3, which simply implies that 1 over square root of 1 plus c e to the power 0 is equals to 1 over 3. And then simplifying this, we can see that this is simply equivalent to saying 1 over square root of c plus 1 is equals to 1/3. Now squaring on both sides here, we get that 1 over 1 plus c is equals to 1 over 9. And again, inverting on both sides here, we get that 1 plus c is equals to 9. And then we can say, therefore, c is equals to 8. Subtracting on both sides, or adding on both sides, minus 1 here. You get that. So then our final answer now, y, the unique solution is y equals to 1 over the square root of 1 plus 8 e to the power 2x. And that will mark the end of the solution. So we've done everything. I hope you have followed all the steps from A up to Z here, and you've experienced the procedure. But if you haven't, you have to go through this presentation again and follow them so that you can be able later to do any of the problems which is here. If you have any challenges, you know what to do, you can contact me and consult for on whatever is challenging you. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wells Msipa.